Welcome back to the discussion portion of Lab 2. So we're going to talk about Part A, which is the homeostasis and negative feedback section. That's FOX 1.3. And Part B, that's the acid-base balance and respiration portion, which is 8.4 FOX. So we'll go through each one of these and sort of connect them to physiology and things like that. As I said in the first video, one of the more important aspects of this lab is to pay attention, one, because you should, but with in the back of your mind, if you're going to use one of these for your lab report. As I said before, your lab report, you have 5 labs to do from this one, which literally is every little section. So when I say a lab, I'm not talking about 1.3 FOX, I'm talking about 1.3A of FOX or 1.3B. So any of the 5 labs that you see here are all fair game in terms of one of those doing your lab report on. The other 3 are going to come from lab 3, which we'll do obviously next. And in lab 3, that will be the plasma concentrations, and you can choose either glucose, cholesterol, or protein. And from these 5 and those 3, that will be one of the topics for your lab report. So you just have to choose one, but those are the only 8. So pay attention and see which one you want to do more of and which one you think is more interesting and things like that. I think they all have some advantages and they all have some disadvantages, but altogether they tend to work pretty well. Probably the hardest one to do of all of them is 8.4A buffers and pH. And I just don't think that students understand pH and buffers as well as they should often in order to do that one. So I think that one tends to be a little harder than the other ones, but I think they're all really good and have some advantages and disadvantages. So just that's an aside and something to think about as you do these for the future. So we'll start with discussion of 1.3A and just kind of work through them consecutively as we kind of did them in the last video. So remember, there's the first part, and that shows the experimentation and the data, kind of talks about what we expect to get the data, and then the second part, which is a discussion of why that is and what the implications are physiologically. Also note at the end of each lab in the supplement, there's sample data. That's the data we're often going to use and kind of talk about in order to discuss what's going on. So if you remember, in the first video we talked a little bit about the water bath. The water bath is what they call a constant temperature water bath, and water baths are used to keep the temperature at a stable point. Water baths, in the vast majority of situations, only have a heater, and so there's a bunch of reasons for that. One is price. A water bath with a heater and a cooling mechanism both cost at least 10 times more than a water bath with just a heater, but they're not really practical. So usually the temperatures that we are concerned about for keeping the reactions a similar temperature would be like a freezing point, which you could just use ice water to get that. A point where you have something at room temperature, you can just use the room for that. And then sometimes, warmer things, right? So typically the room temperature is, somewhere between 18 and 20 degrees Celsius, typically. And then I think most of you probably remember from other courses that 100 degrees Celsius is boiling and 0 Celsius is freezing point of water. And, the other, 2 big numbers to know for temperature would be 37 degrees Celsius. That's body temperature, so similar to 98.6 in Fahrenheit. And then the other big one sort of is minus 40 So 40 degrees below zero is the same temperature in both the Celsius and Fahrenheit scales. So when we look at a water bath, they only have a heater in them practically. And in order to test sort of how well it controls temperature, is we got the temperature of the water bath, got it to temperature in what we thought was 50 degrees. Ours wasn't fancy like this one. It doesn't have a digital readout. It actually has what they call a voltage regulator rheostat, much like the scale on your microscopes you've used in the past, probably that light intensity knob. What it does is it changes the voltage, and if you have more voltage, you have a greater increase in heat. So we don't have one that just says, oh, we want 23.32 degrees or whatever it is on this water bath you can see here. We just by trial and error kind of get to the temperature that we want, and by knowing from experience what it is, I know what to set it to in terms of that little dial, because it's like like I said, the microscope dial that just has numbers on it, doesn't have actual temperatures on it. So, what's important about homeostasis? So, body temperature is one of those things that is homeostatically controlled. There are many variables in the human body that are homeostatically controlled. Two that we are looking at today, body temperature is homeostatically controlled, as is blood pH. Blood pH is homeostatically controlled around 7.4. Blood glucose is homeostatically controlled around 70 to 100, probably 110, even 115 or 20 in some people, milligrams per deciliter. So that's another important control point, variable. Blood pressure is homeostatically controlled variable. So there's a number of them in physiology that we're going to talk about this semester. And what homeostasis means the maintenance of a constant internal environment, that we need to maintain a constant internal working conditions of the body in order to function optimally. And so temperature, pH, blood pressure, blood glucose, there's a bunch of other ones, but those are probably the big four for this classroom for the most part, and especially the two that relate to today. So how does a water bath differ from the human body? And so let's kind of look at what we did in class. We took the water bath, turned it on, right? Watched the red light go on to show the heater was going on. And as the heater heated up the water within the water bath, it was constantly measuring it. And once the temperature reached our set point, the temperature we're trying to get, in the case of the lab data, close to 50 degrees, can't get it exactly on because of the way that water bath works, as I just explained, the heater turns off, right? And so once the heater turns off, we were supposed to measure that temperature for 5 consecutive readings. And when we did that, it was 49.7. The data's in the supplement, 49.8, 49.8, 49.8, and then 49.9. So those are all degrees Celsius. So if you take the average of those 5 points, that you can kind of consider your set point, the point at which our temperature will fluctuate around. And as long as that temperature is in that area around the set point, then our water bath works fine. Okay, but when the temperature gets outside of that set point, then we have mechanisms that kick in to bring the temperature back. So for the water bath, what happens is once the heater goes off, even though the water bath is insulated, it's going to lose heat to the environment. It's going to lose heat to the classroom. And as it loses heat to the classroom, the temperature goes down. And eventually it goes far enough away from the set point, from that average temperature it's trying to maintain, and the heater kicks back on and it brings the temperature back up. To demonstrate that, we dumped in a bunch of water, and we had ice water. As we dumped in the ice water, it wasn't that much ice, so it wasn't like zero, right? But it was pretty cold, and that dropped the temperature. So it went from, you know, an average of 49.8 degrees down to 37.6 degrees Celsius, because we dumped in a pretty big chunk of ice water. Well, when it does that, the heater turns back on and it heats the water back up till it reaches that set point again, that average temperature right around 50 degrees Celsius. And so that's a great example of what we call negative feedback. Negative feedback is when you move away from the set point and then bring the variable back towards the set point. So that's called negative feedback. And that's how homeostasis works. The problem with the water bath being a good example of homeostasis is that when we go the other way, and we didn't do this, but if we took boiling water and once the water bath got back to its temperature, the boiling water was dumped in. So the temperature of the water bath now at 50 degrees or so is going to increase. And when that temperature increases, the water bath has no mechanism, because it's only got a heater, to lower the temperature. I mean, it's going to, dissipate to the environment, but it's designed to be fairly well insulated, so it has no mechanism to actively bring the temperature back down. And so the water bath is not a good example of homeostasis because it only goes in one direction. And the key term of that is called antagonistic control. Okay, so in the human body, for all those variables I mentioned, we have ways to bring the temperature of our body, as an example, back to the set point. So if our set point is 37 degrees Celsius and we got too cold, we have ways through negative feedback, to bring it back up. If we got too warm, we have ways through negative feedback to bring it back down. So we have what's called antagonistic control. We can go in both directions, right? So kind of the definitions I gave you before: homeostasis and maintenance of a stable or constant internal environment, right? We have a set point, that's the target value, right? A couple things about set points: they can be altered, they fluctuate daily. So depending on whether there's daylight or darkness, whether it's artificial or real, right, your body temperature fluctuates. Look, it fluctuates very nicely with those things. So we have different set points in different places we maintain our body temperature around. Our blood glucose changes as we eat. Our blood pH changes as we make more or less of acids and things like that, or breathe more or less. So we do have the ability to change those homeostatically regulated variables I mentioned before: blood pressure, blood pH, temperature, things like that, blood glucose, by moving it back to the set point from either direction. Okay? So they're said to be in what's called a dynamic equilibrium, where the parameters fluctuate within a narrow range around that set point. So the set point is the point that we adjust things to from that. So as an example, your temperature is not always exactly 37 degrees Celsius. Its set point fluctuates around. Temperature fluctuates as you get a fever, as an example. And a fever is when your body resets the set point to a higher level so that the temperature fluctuates around that level. So one of the key components to having homeostasis is the antagonistic control. Right? You need to be able to go in both directions. You need to be bidirectional. For our experiment within the classroom, the water bath is not bidirectional. And here's kind of a nice little schematic of it. So we have a heater, right? There's a thermometer that measures the temperature. So that's what we use to set the thermometer to whatever temperature. That's the set point. That sends information to a control box that's called the integrator. Okay, and the integrator is always saying, oh, the temperature's fine, the temperature's fine, the temperature's fine. When we dump the ice water in, right, the thermometer would say the temperature went down, the control box would say it's gone down too much, kick on the heater, and that'll bring temperature back up. So it's got a sensor, it's got an integrating center, that's the control box that takes in the information and decides on action. So if it fluctuates too much from the set point, the control box turns on the heater, and the effector, that's the heater that mediates the response. So your body sort of does the same thing. From a standpoint of human physiology, the thermometer is primarily our hypothalamus. The hypothalamus is our portion of the brain that's not subjected to the blood-brain barrier, so we can measure a bunch of things there, and one of them is temperature. All right, and if your temperature goes too low, right, then you will signal various outputs to try to increase your temperature. Your brain will have behavioral problems, not problems, behavioral changes, I guess is a better way to say it, based on that problem. Where it's, okay, if you're out in the cold, get out of the cold if you can, or put on a jacket if you can, or things like that. But also it will start to change blood flow and maybe cause, shivering, right? Shivering is what we call scientifically sometimes thermogenesis, generate heat to try to increase your body back to a normal temperature if you are too cold. So, we have these control systems in place, not only within the water bath, but also within the human body. So there is some crossover, but the key component is it lacks antagonistic control. And in order to have negative feedback work effectively, you need to have it in both directions. Okay, so here's an example of temperature fluctuating around 30 degrees, right? And as it goes down, we have mechanisms to bring it up. And if it goes too high, we have mechanisms to bring it back down. And we're always going to be fluctuating around this middle set point, the little normal range of function, that's our set point. So negative feedback is not just when it goes down to bring it back up, it's also if it goes up to bring it back down. So we need that bi-directional correction in terms of our variable, and the water bath does not have that. That's why it's not a good example of homeostasis. The other part of 1.3 in FOX 1.3b was looking at pulse rates. And in that last video, I asked you to take your pulse rate and, 5 times. It's probably not a bad practice. For some of you, you're going to do it for a living eventually as you become nurses and things like that. It's constantly taking pulses, especially at the wrist. But also to get a little practical when we can, work on a little practical knowledge. And so if you haven't done it yet, you should take your pulse rate 5 times. We take it for 15 seconds. That's sort of standard. There's a bunch of reasons for that, but most people get bored after 15 seconds and their mind starts to wander and they don't become as accurate in the count. That's part of it. And then obviously if it's 15 seconds, you multiply it by 4 because typically we report pulse rates in beats per minute. So again, if you look at the sample data within lab 2, right, we have somebody in lab who had their pulse rate taken just by themselves and a couple other people. And so as they go across, 17, 18, 19, 17, 17 are the numbers that you see in the lab supplement. You should open it up and look at it if you haven't. And then 17 times 4 is 68, and 16 times 4, 18 times 4, looking at the numbers, 18 times 4 is 72, and so on. And the idea would be get the minute pulse rates 5 times, and then take an average of that. That would represent, theoretically, your resting set point. Okay, so then you take the average. What we would do then is just say, okay, that's your average pulse rate, and then we decide whether or not you're an exerciser. So you would decide that, and what we'd do is we'd calculate an average pulse rate, and then you go, okay, do you exercise minimally? And it's difficult now because your life is way different this week than it was a year ago this week, right, with the pandemic and things like that. But even then, if we weren't in a pandemic, right, your life is probably different at school than it is at home. And so it's hard to kind of calculate, but you need to estimate, are you a habitual exerciser? And are you exercising at least 3 times a week for at least 20 to 30 minutes where your heart rate gets up and it makes it more difficult to breathe. If you're not one, then you would put yourself in the column that is not an exerciser. So here's some personal data, just one person. This obviously wouldn't be yours. And put that information into a table. And heart rate is controlled by negative feedback, and that's kind of interesting. I think that you probably understand that at least a little bit from your anatomy, although it's much more complicated than you probably were told. But as you know, the primary controllers of heart rate through negative feedback would be the autonomic nervous system, both branches, right? So if you remember, and we'll hit this a lot this semester, the sympathetic nervous system, right, increases heart rate if we stimulate it more. If we stimulate it less, it decreases heart rate. It's sort of like the accelerator to your heart, or similar to the accelerator to a car. On the other side of the coin, the parasympathetic system, if you stimulate that, it decreases heart rate. But if you withdraw it, then it increases heart rate. So heart rate is controlled with these negative feedback mechanisms. Okay. What's interesting is heart rate is not homeostatically regulated. So just because you have negative feedback does not mean it's part of a homeostatically regulated variable. Right? We actually use heart rate to control blood pressure. So we adjust heart rate up or down to increase or decrease blood pressure. We'll see that later on semester in the cardiovascular system when we talk about the cardiovascular dynamic stuff. But blood pressure is homeostatically regulated, not heart rate. So here's kind of a nice note to put in your head. All homeostatic mechanisms utilize negative feedback, right? And that's in bi-directional terms. They have antagonistic control. But not all cases of negative feedback necessarily involve a homeostatically regulated variable. All right. So you look and say, okay, is this individual's heart rate normal? So for the average heart rate, right, you just add 68 plus 72 plus 76 plus 68 plus 68, right? And you see what that number is, and then you divide by 5, and you get, so what is that? It would be 352 divided by 5 would be 70.4, okay? So normal range of heart rate is typically 60 to 100. Athletes have heart rates that generally are lower. Okay, so we'll see someone who's a really, really world-class athlete might have heart rates as low as 25 to 40 beats per minute. And those variables depend on a number of different things. Genetics, body size, your sex, your level of fitness, and a few other things all influence what your resting heart rate would be. One of the variables we'll talk about later, so we'll learn it now, is something called cardiac output. Cardiac output is the volume of blood pumped out of your heart per minute. Okay, so we all have a relatively same need for cardiac output, depending on factors. Obviously, the bigger you are, the higher cardiac output you're going to need at rest because you just have more mass. But it doesn't matter whether you're trained or not trained. For the most part, people who are fit have the same cardiac output of someone with similar size who is not as fit. So what happens is cardiac output is the product of stroke volume and heart rate. Stroke volume is measured in mLs per beat and is the amount of blood pumped out per beat. So every time your heart beats, it pumps out an amount of blood. So that amount of blood is called stroke volume. And the other variable in question is heart rate. I think you understand that, right? That's how many times your heart beats per minute. So if you mathematically look at the equation here, right, mLs per beat times beats per minute, the mLs cancel out, the beats cancel out, and you get mLs per minute. So that's the unit of cardiac output. So our cardiac output, as you exercise habitually, your stroke volume goes up. You become a stronger beating heart. right? The muscle mass probably actually gets larger over time and certainly is more effective as a pump. If you are pumping more blood each beat, you're going to need less beats to pump the same amount of blood, right? It's like getting a job. If you need to make $1,000 a month to, make ends meet, and you get a job that gives you $10 an hour, right? You have to work 100 hours a month to do that. But if you get a job that makes $100 an hour, you only need 10 hours a month to do that. So the cardiac output, as that changes, your heart rate's going to change. And again, with exercise, not the exercise itself, but because of the exercise, your cardiac output's going to go up because your heart's a better pump. And that means your heartbeat at rest is going to go down because you need less beats to pump the same amount of blood. So the cardiac output requirement for everyone is similar. It's about 5 liters per minute of blood. And so as you increase fitness, you increase the stroke volume because you have a stronger heart, and you decrease heart rate to maintain the same cardiac output. If your fitness is lower, you have a lower stroke volume, and you increase heart rate to maintain the same cardiac output because you need more beats to do that. Now, before we go on, let's talk a little bit about some of those factors. Again, I'll go backwards in the slide. How do these other things influence heart rate? So just because you have a low resting heart rate doesn't mean you're fit. And just because you have a high resting heart rate doesn't mean you're unfit. Okay, so you can't just say, oh, your heart rate is high, you're fit. And again, going back to the first lecture, that's an ecological fallacy, attributing the traits of a group to an individual. Okay, but it is dependent upon a number of factors. So we just talked about fitness level and increasing the stroke volume because you have a heart that's a better pump, which then causes the heart rate to decrease. This was one way to affect your heart rate, your rest at rest. Your genetics plays a role. Some people, I think all of you remember this from your anatomy course, probably, but the sinoatrial node, the SA node, which is an area in the upper right portion of your heart, right above the corner of the right atrium, that has special tissue. It's called autorhythmic tissue. We'll talk about that when we get to the heart physiology later on in the semester. And I think you all realize the SA node, in normal circumstances, sets the basic heart pattern. Okay, so your SA node sets that basic heart pattern and serves as the pacemaker for the heart. Some people just have a naturally fast or naturally slow SA node. The way to get to what its real rhythm is to cut it out, but I don't think anybody wants to do that for theirs. So most people's SA nodes fire somewhere between 60, 70, and 100 beats per minute. And then that's modified by the other factors. So you have this inherent basic rate. So if you have a fast SA node that's inherently just fast, your heart rate's going to be higher, whether you're fit or not. If you have a slow SA node, your heart rate's going to be lower, whether you're fit or not. Size makes a difference in this case. Larger humans have slower heart rates than smaller humans. If you've ever been to a birth, oftentimes they measure the baby's heart rate during delivery, and it's pretty high. It's often in the 120s, 130s, 140s. Part of the reason is babies have a naturally faster rate because they're smaller. Also, obviously, it's higher because they're under stress during delivery. But the point being that as humans grow in size, the heart rate tends to decrease. And that's actually true of all animals across, especially mammals across that. So the smallest mammal is often cited as what they call the Etruscan shrew. It's about the size of your pinky as a full-grown adult. And it has a heart rate that's probably 1,500 beats per minute. So really, really fast. The largest land animal, an elephant, has a heart rate about 12 to 15 beats per minute. So literally, hundreds of times faster in the smallest mammal versus the largest mammal. So humans reflect that as well. So size. Sex. For whatever reason, females tend to have a faster heart rate than men. Some of that is attributed to changes in levels of hormones, but not necessarily just levels of hormones. in terms of that. So sometimes those different levels of hormones do play a role, and sometimes it's just because we can't figure out what it really is due to. So, but females, independent of the SA node and independent of body size, have a slightly faster heart rate than males on average. So as an example, if you had a very fit female who was small, right, and had a fast SA node, her resting heart rate could be 100 beats per minute, and she could be in great shape. While you could have a large, unfit male and had a very slow SA node and wasn't fit at all, could have a much slower heart rate. So you can't just say, oh, your heart rate's fast or slow, that you are fit, right? So you have to look at other variables and things like that. So the key take home for this is, a couple, you should be able to figure out for Fox 1.3, you should understand what negative feedback is, what homeostasis is, why the water bath is sort of an okay example of homeostasis in some ways, but a terrible example in others, and that's because it lacks that antagonistic control for negative feedback. For the second part, right, you should understand how to measure an average heart rate, what an average heart rate would be, what factors determine your heart rate, and then why someone who's fit would be expected on average to have a lower heart rate than someone who's not. So I think it's probably not a bad idea to split this up into 3 separate videos. So we'll end this one and start another one for 8.4.